Welcome to another Lightblade Learning Lab. Today we're going to give you a bit of a look at the anatomy of this vital part of the machine, which is the laser tube itself. Now it's quite important that you understand how this basically works, because you need to look after it. Now you haven't got to do anything to it other than treat it well. But why do you have to treat it well? If you understand how the tube works, you will understand how you can abuse it. And that's the last thing I want you to do, because if you abuse that tube, it's going to cost you several £100s to replace it, and it won't be under warranty. You may be interested in a couple of lights that I've got stuck in here at the moment. These are just what I call my winterizing kit. Tucked down here, I have a small temperature controller, or a temperature controlled relay, which is looking at the air temperature inside the machine. This workshop that I'm in is totally unheated, and during the winter months I'm fearful that the water that's inside this tube may freeze. So I've taken some special precautions of adding 100 watts of heating into this machine and 100 watts of heating down there to the chiller unit as well, so that during the cold winter months, as a completely separate supply, this machine will heat up the water in this tube and circulate it through the pumping, so there is absolutely no chance that anything will ever freeze. Okay, now this tube is actually made up of 3 glass tubes. The first outer tube, which is what I'm tapping at the moment, is the container for the gas. That's a gas reservoir. Now inside there you'll see there is another tube, and if you look carefully you can see along the top of that tube some little air bubbles. Well, that's the water jacket that sits inside this outer tube here. And then if you look a little bit closer, you may find through the reflections that there is a third inner tube that you can see. Now the third inner tube is the containment tube for the ionized gas. Okay, now down at this end of the tube we've got this red cable, very thick red cable, which is capable of taking, I think, about 40,000 volts, but it's a 25,000 volt cable, this one. And this cable goes to that blue electrode there, which is the anode. But when this tube is working, the gas tends to flow towards this positive electrode. It returns and comes back. Can you see that pipe there that's going across the top? You can see the spiral tube here. Now that basically is spinning the gas round, and then it deposits it just underneath this label here. The gas is spinning around at that point in time, and it travels back along the reservoir to the other end of the tube. So there's always a circulating flow of gas through this tube. Okay, now I talked about a gas reservoir, this outer tube being a gas reservoir. Trace gases like hydrogen and xenon and 1 or 2 other mixers may be in there as well to help certain aspects of the tube. But these are the principal gases that you need to imagine operating within this tube. The nitrogen is actually the most important gas. Now you might say, well, this is a carbon dioxide laser. Surely the carbon dioxide is the important gas. Well, yes it is, but let me explain that the nitrogen is absolutely fundamental to the way in which this tube operates. Now I'm not going to turn the tube on at the moment, but when we turn the tube on, you will notice that there, as I've shown you in the first introduction, you will notice that there's a pink glow along the tube. Now that pink glow is actually ionized nitrogen. All of these gases are non-conductors naturally. Even as it's sitting there, this tube is being bombarded by cosmic rays from the sun. I know it's night time, but they pass through the earth, they pass through anything and everything, and there will be some cosmic rays which will actually be colliding with some of the nitrogen atoms that are in that tube. There might only be 1 or 2 or 3. That's enough to start a chain reaction off at any point in time that we wish to turn the laser on. Now to get current flow you need basically some free electrons, or electrons that are knocked out of their orbital shells. Let's not get too involved with the atomic physics because I'm certainly not a physicist. So what's going to happen is, to get this tube kicked off into action, at that end of the tube over there, we're going to put 25,000 volts DC. And that means that there's 25,000 volts difference between that end of the tube and this end of the tube here, which is the cathode. Now, that means that any negative electron which is floating around in that tube, and as I said, there will be some floating around in there just because of the natural action of cosmic rays, those free electrons will immediately start flying at a very high rate of knots along the tube towards that electrode at the other end there. And in doing so, it's like a fat man at the back of the room rushing to the front of the room to get his free hamburger. As he goes, he's going to knock people out of the way. He doesn't care. And that's exactly what happens to these free electrons. They're going to rush towards that end of the tube there, and in doing so, they're going to knock some more electrons off of other nitrogen atoms. And what that's going to do is cause a cascade action, which sets the whole thing in motion, and we can start to get this process called ionization. Now, when the gas starts to ionize, which is basically lightning, the gas changes from a non-conductor into a conductor and can conduct huge amounts of current. We can't afford to let that to happen because the tube would just pop. So built into the system, there's a control system in the power supply which limits the current to a very small value. So we get very small controlled currents running through this very conductive gas. Okay, so we've got nitrogen, which is now a conductor. But it's more than a conductor because it's now an ionized gas, and you don't get ionized gas for free. It requires energy, and that energy produces heat. Now, lightning sets fire to trees. What we've got is controlled lightning, effectively. I'm exaggerating slightly, but we've got controlled lightning in that tube there. The ionized gas can get up to thousands of degrees C. To try and control that temperature, what we've got is two things. The first thing we've got is helium, and we have huge amounts of it in that mixture. Helium is a very, very good conductor of heat. So the helium will carry the heat out to this water jacket, and we've got water flow that passes through the system to take the heat away. So that's where the water jacket comes into play. So the helium is very important, the nitrogen is very important, and we haven't mentioned the CO2 yet. Let's just go back to the nitrogen for a second, because I said it was the most important gas. Without the nitrogen ionizing, we don't get anything happening. The nitrogen atoms are in fact being, let's imagine, excited. My hand is moving to imply excitement, all right? And when this is running at a controlled current, let's just say 4 milliamps, we've got controlled excitement. But as we increase the current in that tube, the excitement level of the nitrogen starts going up. And so consequently we get higher and higher energy levels and vibration levels within the nitrogen itself. And we can control the level of that excitement with the current flow that we put through the tube. I can hear you getting impatient. Yes, I know, I don't want to hear about nitrogen. I want to know where the carbon dioxide comes in. Now, I like to imagine the carbon dioxide as a very lazy gas. It doesn't really want to do much. But unfortunately, the nitrogen doesn't want to work that way. It's getting very, very excited. And as it gets excited, so from time to time, some of these nitrogen atoms will collide with the carbon dioxide molecule. And as it hits the carbon dioxide molecule, it will impart some of its energy to the carbon dioxide. And so the carbon dioxide will all of a sudden have to be raised up to a slightly higher energy level. Now, it doesn't want to be there. It's naturally lazy. And so consequently, what will happen is, once it gets excited, it says, I don't want to be here. And it finds any and every opportunity to get rid of its extra energy and go back to sleep again. Now, it is that process of getting rid of the energy, and it gets rid of the energy in the form of light, photons of light. That process of giving off its energy as basically the emission of photons to give off energy. Three other parts of this word laser, and it's called light amplification by stimulated emission of radiation. Well, the stimulated bit is the nitrogen raising the level. The emission is when it drops back down again and it gives off this radiation, which is light in the form of 10.6 micron radiation. We've got this bit at the front here called light amplification. So how's that bit working? Hiding behind this water jacket here, right on the end of the tube, we have a mirror. It's a mirror that is perfectly aligned with another mirror right at the other end. Now this is 100% reflecting mirror. Now at this end of the tube, we've got a brass water jacket, but behind that brass water jacket just here is another mirror. And this mirror is not quite the same as the mirror at the other end. This one is a partially reflecting mirror. I don't know exactly what degree of partially. It may well be 70, it may well be 80% reflecting. But that means that 20% of the energy that hits this will come out of here and will be the laser beam that we are going to use. We talked about the fact that the CO2 gets raised to a higher energy level and then wants to get back down to its lazy level. Now, it only needs one of these CO2 molecules to lose its energy and emit a photon, and that photon will start travelling along this tube in a direction and will automatically persuade another photon to come and join it, i.e. it will trigger a chain reaction, and that chain reaction will trigger more and more photons to join in and travel in this direction. All those photons will start travelling along the tube, and as they travel they will gather more and more photons, and they're all travelling in that direction. So they get to that mirror at the end there, and then they start all coming back. Now there's a lot more coming back than went down. So those coming back, by this time of course we shall have more and more collisions with nitrogen atoms, which have promoted more and more CO2 atoms up to high levels. So as they come back, they will trigger more and more photon release, and you will get a bulk of photons that will gradually be amplified every time they bounce back and forward off this mirror. So we get this amplification of light going backwards and forwards in this tube. It's nothing to do with the light that you see coming out of the centre tube, which is the pink light from the ionised nitrogen. Nitrogen is completely separate from this other invisible light which is bouncing backwards and forwards inside this tube. So there's several strange processes going on here. If you remember at this conversation beginning, I said to you that the current is being controlled by the power supply, and you in fact are controlling the power supply through the percentage power that you input through the keyboard. Now if you put too high a percentage power, you allow more current to flow through that tube. What's actually going to happen is the nitrogen is no longer going to do that, it's going to do this. It's going to go absolutely bonkers. The more current you put through it, the harder it vibrates, the more energy it has. Now you get to a certain critical point, and that is the limit specified by the manufacturer of that tube, and that energy level in the nitrogen is so high that it won't just encourage the carbon dioxide to go up and not be lazy and have a little bit of extra energy. It will have so much energy that when it collides with the carbon dioxide molecule, it will break it down into carbon monoxide and a free oxygen atom. Now carbon monoxide is not a lacing gas. Oxygen is not a lacing gas. So now, because of your enthusiastic use of 100% power, 90% power at the keyboard, you're actually destroying the tube itself, the gases inside the tube, by overdriving the nitrogen and making it far too excited so that it actually has killer powers. I don't want to exaggerate that too much, because built into the system there is probably some hydrogen. There's probably in that particular tube a catalyst, which is gold, which actually partially reunites these two back together to make that. So there is a healing process that's built into some of the better quality tubes. and that helps to promote a longer life tube. The principle of a tube dying over a period of time is basically this one, because even when you're running the tube under manufacturer's specified control limits, there is a very small amount of this dissociation, as they call it, taking place. So both the gold and the additional gas, which is generally hydrogen or water vapour, has got a catalytic effect of recombining these two back to carbon dioxide. But drive it too hard for too long and you will permanently destroy the carbon dioxide, and what will happen is the oxygen will tend to collect on the cathode at the end there and change the colour of the cathode. And so it will be obvious that you've been a naughty boy and that you have destroyed your tube by overdriving it. So I can't say any more than that. Now you know how the tube works and why you can overdrive the tube. You can make the mechanism work harder than it should do. There's a balance point that you mustn't go beyond. I happen to know that this tube is made by EFR Laser and it's a 1200 CL. So we can go to the website and we can find out what current specification they recommend for this tube. Now my guess it's somewhere in the region of 22 to 25 milliamps. One of the quickest ways of finding out the relationship between this 22 milliamps and the amount of power that we're allowed to use is to probably just use the pulse button. We can set the maximum power here to some value. I will show you how to do that shortly. And we can check whether or not the power that's on here equals 22 milliamps. So it may be that we'll only be able to put 60% power into here and we should get 22 milliamps. Now what that means is you've already reached the limit at 60% power. At no time can you ever program into this machine more than 60% power.